So this video is going to discuss the differences between the mean and the median. We saw an example of finding the median for 8 college students' summer job hourly wages. Now let's find the mean of this data set. Right? If we were to find the mean of this data set, this is a sample. So we would end up denoting this as X bar. But here we have 8 observations. So we would add up all of those 8 observations, including this new student who apparently makes $128 an hour, and divide by the total number. And if we were to do that out, we would end up with the value 30. And we would denote this as X bar, the mean of a sample. Now by looking at these two metrics, the mean, which is 30, and the median, which is 16, which one do you think better represents a typical observation in your data set? Pause the video and spend a couple of seconds to figure that out. Hopefully you've come to the conclusion that the mean is not doing a good job of representing a typical observation. Nobody makes around $30 an hour. The median, however, of 16 represents a typical observation. A lot of people seem to be making around $16 an hour. What's happening is this mean is being influenced strongly by that $128 an hour student. We would consider that an outlier. Now, in later videos, we'll talk about how do we determine an outlier. But for right now, that 128 looks like it's an outlier, and it's throwing off our mean, whereas the median is not affected. On top of that, imagine instead of having a student that makes $128 an hour, imagine we had maybe, I don't know, Mark Zuckerberg himself's hourly salary of $128,000 an hour. Oh boy. Well, is that going to affect our mean at all? Well, now that last value is $128,000. This mean is going to skyrocket up. Our median, however, we still have 8 observations. We still have that location of 4.5. So we'd count 1, 2, 3, 4.5. Our median is the same exact value. It didn't matter whether it was 128,000 or 128. Our median stayed the same. What we just witnessed is a concept called robustness. Robustness represents how resistant a statistic is to outliers, influential points, or errors. And so what we just saw when looking at the mean versus the median is the median didn't care about that crazy value at the end. Whether it was 128 or 128,000, it wasn't affected. The mean, however, was affected. So when we look at these two measures of centers, the median is more robust than the mean. So not only does robustness hold true for an outlier, it also involves the shapes of distributions. So one thing that's very common is you'll have data that is skewed. So if you have skewed data, for instance, we talked about this shape, this is right skewed data. And so what you have here is you have some observations, not a lot of them, a couple observations that are very large compared to everything else. They're not necessarily outliers because that's kind of where your data is trending. But they do have extreme values in terms of the size of them compared to others. So what happens is even though there's only a couple of them, your mean gets drawn toward these larger numbers. So if this was a set of data, your mean might be over here. Your median, however, as we saw, doesn't care about the size of these numbers. This number can be very large, this can be extremely large. Your median isn't affected by that. It just cares about the middle number or the middle two numbers. So your median may still end up being over here. When you have skewed distributions, your median does a better job of representing a typical observation because it's more robust. If, however, you have a distribution that's not skewed, maybe we have a bell-shaped distribution, maybe we have a uniform distribution, or maybe we even have a kind of bimodal distribution. In these three cases, if you look at the mean and the median, your mean would be right smack dab in the center, and your median would be smack dab in the center. And that would be true for all of these symmetric distributions. Your mean and median would be exactly in the same place. So for a distribution with an outlier, or a crazy outlier, your median can do a better job of representing a typical observation. For a skewed distribution, your median can do a better job of representing a typical observation. When you have a symmetric distribution, your mean and median end up in the same spot. A lot of people grow up with this notion that the average is this holy grail of numbers. And there's definitely some benefits of looking at an average, but we shouldn't be quick to throw away the median. It does a good job of representing a typical observation in almost all your situations. So what we need to consider is, if we're trying to represent a typical observation, when should we use the mean? Because it seems like either the mean does the same job as the median or a worse job. Pause the video and spend about 30 seconds to a minute thinking about when would we like to use the mean as opposed to a median when representing a typical observation in regards to the shape of your distribution. All right, we're back. So for this class, we're going to go over the one situation where the mean can be doing a better job of representing a typical observation. And it actually has to do with symmetric data. Now, if you were to talk about the mean of a population and the median of a population, you can see that they're the same exact value. One is not better than the other. However, typically, we don't know these values. These are mysteries to us. All we have to go on is a sample mean and a sample median. So when we have a symmetric distribution, it's going to turn out that we're going to want to use the mean of a sample when trying to represent a typical observation. And the reason being is this: when we find the mean, right, what we do is we take every single observation's value into account. Every single value gets taken into account. Compared to the median, where we only look at the middle number or middle two numbers. Only two numbers' actual values are being taken into account when we come up with that metric. The mean is using every single observation's value. And because you use every single observation's value, you'll have the ability to become more precise. You can get a more precise estimate when looking at the mean of a sample compared to the median of a sample, because it will be able to take on more values. More values are going into it. It can yield a more precise measure of your center. If you knew the population mean or you knew the population median, then you can use either one because they're the same exact value. Either one would work. But when you have a sample of data and you have a symmetric distribution, that mean will be more precise because it uses every single observation's value to come up with its metric, compared to the median just uses one or two numbers. So this is the situation for us when we're thinking about a typical observation, where we're going to want to use the mean as opposed to the median.